Hey, I'm Stephen Cox. I'm an Emeritus Professor at the Research School of Earth Sciences here at the ANU. My research interests are really in studying deformation processes in the Earth, but particularly about how fault processes, earthquakes, influence fluid migration paths in the upper crust. That has two important things because fluid migration can influence formation of earthquakes, nucleation of earthquakes, but also faults act as fluid pathways to generate ore deposits. My interest has long been in deformation processes in the Earth, and probably 2 decades ago I became very interested in how fluids were coupled with the deformation process. And gradually, as I got into doing the field observations, I thought, okay, we've really got to look for modern analogues of this. How do these systems behave in the modern Earth? And that drew me into looking at earthquakes, and gradually I realised that when people do deep fluid injection experiments, for example, in Central Australia they've done some in Europe, in various places in the US. When you inject fluids into those rocks, you generate what we call earthquake swarms, which are very different from the main shock, aftershock we hear about in the media when a big damaging earthquake occurs somewhere. Swarms are sequences of typically very small earthquakes, ruptures maybe only about up to 1 kilometre or so, and there may be thousands to tens of thousands of them occur during fluid injection over maybe a week to a couple of months, something like that. And they're very small earthquakes, and we realised from these injection experiments that that's the typical behaviour that occurs when you inject fluids into what we call tight or low permeability rocks. Having got some of that data and studied, I was like, okay, can we search for these in the modern Earth, not engineered ones, natural ones? And I very quickly started discovering that in places like Japan, a nice example in Western Czechia and various other places around the Earth, California and the western part of the US, there are these common earthquake swarms which have this characteristic behaviour of many thousands of earthquakes in a short period. And the biggest one can be magnitude 4 or so, often down to really tiny ones at magnitude -1, -2 can sometimes be detected. And they'll occur over a few days to a few weeks, and the earthquakes migrate with time at rates of hundreds of metres per day. But I couldn't work out how to do time sequencing because time is very important. They migrate with time. And I talked to various people and there weren't easy solutions. And I thought, oh, someone mentioned NCI. So I sent an email and got in touch with Drew Whitehouse, it turns out, and he jumped at it and it evolved from there. He's done amazing things in generate some initial visualisations using the Houdini software, which is what CGI people use in Hollywood. And then he's just developed that technique, and now we have a fully interactive web server where we can just in real time spin these earthquakes around, progress them through time, take slices through, and really come to get into great detail about how these fluid-driven earthquake swarms operate. And that's telling us a lot about how ore deposits form in the real world. It's changed our whole view of these fault-hosted, particularly gold deposits like those in Victoria in Western Australia. We now understand that they form by swarms, and the swarms are actually tracking the migration of the fluid through networks of faults with time. And we know that now from this work that one of these deposits can actually form in maybe 100,000 years or so, produce 50 tonnes of gold, much quicker than we thought. But the fluid flow is only active during maybe 10% of that time because the swarms are switching on, switching off, switching on, switching off, because they wait to build the fluid pressure before a new swarm starts. In complex swarms like those we're studying in Hakone caldera in Japan, it's a very complex network of faults over a crustal volume of maybe 8 kilometres by 4 kilometres by about 6 kilometres deep. And the structure is incredibly complex, and you need really good 3D visualisation to actually understand it. And it's migrating in complex ways through this fault network with time, so that's been a major leap forward. It's very complex, and this has enabled us to understand that complexity. We can quantify the migration rate with time, how the earthquakes migrate through the system and then jump from one fault to another fault. That's been really interesting. But also what we got out of this is there are relationships between the energy release, what we call the seismic moment release during earthquakes, and the amount of fluid that's injected. We've got those relationships from deep injection experiments. We can now take that analysis and apply it to somewhere like Hakone caldera and recognise that on average over a 2-decade timescale there's about 20,000 cubic metres of fluid being injected per year, but very episodically. Drew and his colleagues have just been extremely innovative and done way more than I imagined they could do when we first started this just over a year or two ago. So it's just been incredibly clever. They're tools I could never learn to use myself, so this is fantastic.